In this section, we're going to look at DC or direct current circuits. Okay, what we call a DC circuit is a circuit where the voltage or the current is constant in time. This is a circuit where the voltage or the current is constant in time. This is the kind of voltage you get from a battery. If you plot the graph of the voltage of a battery, it will be constant. Okay, so if you've got a circuit connected to a battery, then the voltage will be constant and the current would be a constant. So a DC circuit, which is an abbreviation for direct current circuit, is a circuit where the voltage or the current is constant in time. Now let's define what we mean by a source in a circuit. A source is a device that converts non-electrical energy to electrical energy. This one is a device that converts non-electrical energy to electrical energy. Example, if you take a battery converts chemical energy to electrical energy. This one converts chemical energy to electrical energy. So a battery is a source. Another example, a generator. This could be a hydroelectric generator. This one converts mechanical energy to electrical energy. This one converts mechanical energy to electrical energy. Okay. So in the previous chapter, we looked at a device that converts electrical energy to non-electrical energy, which is a resistor. This does the opposite. It converts non-electrical energy to electrical energy. Now we're going to look at electromotive force of a source. Electromotive force, which is abbreviated by EMF of a source. This is defined to be the amount of work done by the source per a unit charge. This is defined to be amount of work done by the source per a unit charge. In taking a charge from one terminal to the other. So we can say in taking a charge from one terminal to the other. So mathematically, we can say, let's say we use this for EMF, and let's say we use W subscript S for work done by a source. So and also use Q for charge. So mathematically we can say the EMF of a battery is work done by a source divided by the charge. Okay, it is a work done by the source per unit charge. Okay, now we've seen before the circuit symbol of DC source. So let's do it again. Symbol of a DC source is one short line, one long line. This is a positive terminal, this is a negative terminal. So this is a symbol of a DC source. The longer line is positive terminal and the shorter line represents the negative terminal. Okay. Now let's consider a circuit with a source and a resistor. Okay. A circuit involves a source and a circuit, a source and a resistor. A circuit usually consists of a source that produces the electrical energy and then a device that converts the electrical energy into something else. So a circuit consists of a source and a resistor or resistors. Okay. All right. So let's look at the following circuit. This is the EMF, and then this will be the external resistance R. Okay. Now any source has its own resistance, and that's denoted by R. Okay. Now let's look. Well, this will result in a current. Okay. This positive charge is going to attract electrons from here, or you can say, as you've seen before, conventionally the current is assumed to be carried by positive charges, even though it's carried by negative charge electrons. So if you assume the charge is carried by positive charges, then the positive charge will be repelled by the positive terminal and attracted by the negative terminal, and the current will flow this way. Okay. Well, let's say that current is I, and the EMF of the battery is E. Okay. Now let's look at the potential difference between the terminals of a battery. Let's say this point A, let's say this point B. Okay. Now the potential difference between these 2 points is the EMF of the battery, the potential difference created by the battery, minus the potential difference dissipated in the internal resistor. Okay, according to Ohm's law, that's going to be I times R. So the potential difference across the terminals of a battery, potential difference, we're going to use VAB for this one, across the terminals of a battery. Terminals of a battery is given by VAB. You got the EMF, but then some of it will be dissipated in the internal resistance, and this will give you the potential difference across the terminals of the battery. So even though the source is producing this potential, this EMF potential difference, some of it will be dissipated in its own internal resistance. Okay, so R is internal resistance of the battery, internal resistance of the battery. Okay, now this potential difference is available to the external circuit. Okay, so the potential difference across this resistor R is not the EMF E, but the EMF E minus the potential drop across the internal resistance. So the potential difference across the resistor is not the EMF E, but the potential difference VAB, which is equal to EMF minus R. Okay, so we have the potential difference between the terminals of the battery equals current times resistance from Ohm's law. Okay. Now if you equate these two, we have IR equals E minus IR. Let's solve for the current, so let's take the other side. So you've got IR plus I internal resistance equals the EMF E, and then of course you factor out the current. Okay, that is EMF E. All right, so the current equals the EMF E divided by the sum of the external resistance and the internal resistance. Okay, so R over here is external resistance, and this would be the current in the circuit. If a resistance capital R is connected to a battery of internal resistance R and EMF E. Now let's look at an example. Let's say a battery of EMF, let's say 6 volts, and internal resistance maybe 1 ohm is connected, let's say, to an external resistance of 10 ohms. Okay, let's say A, calculate the current in the circuit. The current in the circuit. Okay, so here's the problem. The EMF of the battery is 6 volts, its internal resistance is 1 ohm, and it's connected to an external resistance of 10 ohms. Okay, diagrammatical, this looks like this. So you've got the EMF of the battery, 6 volts, okay, but then it has its own internal resistance, okay, that is R equals 1 ohms, and this is connected to an external resistance R equals 10 ohms. Okay, and then of course this will result in a current I, and we're trying to calculate the current in the circuit. So let's just show in the previous page, current equals EMF divided by the sum of the external resistance and internal resistance. So this one is 6 divided by 10 plus 1 amps, or 6 over 11 amps. Okay, so this is the current in the circuit. Now B, let's calculate the potential difference across the terminals of the battery. Calculate the potential difference across the terminals of the battery. The terminals of the battery. Okay, so in this case we're trying to calculate VAB. Okay, that is the trying to find out the potential difference between these two. Let's say it's A and B, and that potential difference is the EMF minus the potential drop in the internal resistance. Okay, so we have that equals the EMF minus the current and the internal resistance. Okay, so the EMF is 6, the current is 6 over 11, the internal resistance is 1. Okay, so that is 6 minus 6 over 11, or 6 over 11 minus 6 over 11, which is 60 over 11 volts. Okay, or we can calculate another way. It is, because VAB also equals current times R, right? The current is 6 over 11, and the external resistance is 10, so you get the same thing. So we can calculate either using this formula over here or this formula over here. They both mean the same. Okay. Now we're going to talk about power. Power, if you remember, is the rate of doing work or rate of conversion of energy. This is rate of doing work or rate of conversion of energy. Conversion of energy. So generally, power, we're going to use P for power. Okay. Power is either work done per unit time, okay, or you can say power is energy divided by time, the energy converted in a given amount of time. Maybe you can say delta U for changing potential energy per a unit time. Okay. Now let's look power of the source, work done by the source per a unit time. Okay. So this is power of a source, the source, like a battery. Okay, let's use PS to represent it. This represents the rate of work, of doing work by the source. Is the rate of doing work by the source, doing work by the source. Or you can say it's the rate of conversion of non-electrical energy to electrical energy. Or you can say this is the rate of conversion of non-electrical to electrical energy. Electrical energy. Okay, so using this definition, the power of a source is the work done by the source per unit time. Okay, but remember the definition of EMF, but EMF was work done by the source per a unit charge. So the work done by source is charge times EMF. Okay, so with that we can say the power of a source is Q times EMF divided by T. Okay, but now you see this is charge per unit time, which is current, but Q over T equals current, rate of flow of charge, right? So with that we have the power of a source equals current times EMF. Okay, so this formula represents rate of production of electrical energy, rate of production of electrical energy from non-electrical energy, from electrical energy from non-electrical energy, non-electrical energy. And I is current, and this is EMF. Okay. Now let's look at the power available to the external resistor. Okay. Power, let's say delivered to the external resistor, to the external resistor. Okay, let's use PR for that. Okay, so the power delivered to the external resistor is not equal to the power produced by the source, because some of it will be dissipated in the internal resistance of the battery. Okay, so let's say we have this circuit over here. Now remember, there is internal resistance over here. Okay, so some of the power produced by the source will be dissipated inside this internal resistance. Okay, so this power over here, PR, is power produced by the source, minus power dissipated in the internal resistance, power dissipated in the internal resistance. Okay, internal resistance. So we have this one. The power available to the external resistance is the power produced by the source minus the power dissipated in the internal resistance. Okay, PR is, if you remember, the formula for power was I squared R, right? So we have the power available to the external resistor is the power produced by the source minus I squared times the internal resistance. But also, if you look at this one, you get current I. The power dissipated in this external resistance also equals PR. Okay, this is the power available from source is equals the power dissipated in the external resistance. So this also equals I squared times the external resistance. Okay, so that's how you calculate power delivered to the external resistance, or power dissipated in the external resistance. That was equal. Okay, now let's look at an example. Let's say a battery of EMF 6 volts and internal resistance 1 ohm, let's say, is connected to an external resistance of 10 ohms, like the circuit we used before. Okay, so we have the EMF is 6 volts, the internal resistance of the battery is 1 ohm, the external resistance is 10 ohm. Okay, so let's ask some questions. Calculate the power produced by the source. Okay, so we're looking for PS over here. All right, let's do the circuit. So this is the circuit. We get the positive terminal, negative terminal. We get the internal resistance over here, R equals 1 ohm, and the EMF for the battery is 6 volts, and then this is connected to an external resistance. Okay, let's say this is R is 10 ohms. Okay, and of course this will result in a current I. Okay, so we're looking for the power of the source, but that is current times EMF. Okay, so we have EMF, but we have to calculate the current first. But if you remember, the current is EMF divided by the sum of the external and internal resistance. Okay, so with that we have the following formula for the power of the source, which is E squared divided by the sum of the resistances. Okay, so we're substituting this for I, and then we get E squared over the sum of the resistances. All right, so this would be 6 squared divided by 10 plus 1, which is 36 over 11. And if you remember, the unit for power is watt. Okay, so this is the power produced by the battery. Okay, B. Now let's calculate the power. Calculate the power delivered to the external resistance. External resistance. Now remember, even though this is the power produced by the battery, some of it will be dissipated in the internal resistance. Okay, so the power of the source is the power produced by the source, EI, or we already have PS, minus the power dissipated in the internal resistance. Okay, so well, we have already calculated this one, but this is EMF divided by R plus R. Okay, so this would be E squared over R plus R, just like we did, and this would be the current squared, which is this one, times the internal resistance. Okay, so we have already calculated this one. This is 36 over 11, and this is the EMF is 6, R plus R is 11 squared times the internal resistance R. Okay, so we have, this is 36 over 11 minus 36 over 121. Okay, so well, we can take 121 common, and this will be 36 times 11 minus 36. Okay, so that would be 36 times 10, or 360 over 121. This is watts. This is the power available to the external circuit. Now let's say calculate power dissipated in the external resistance. Oh, this is power. This is PR. I'm sorry. Calculate power dissipated in the external resistance. Well, that's the same thing as power delivered to the external resistance. Okay, that's simply PR. We have already calculated it, and that'll be PR equals 360 over 121 watts. Okay, next we're going to look at combinations of resistances. Combinations of resistances. We've done it for capacitors in the previous chapter. Now we're going to do it for resistances. Okay, as we've seen in the case of capacitors, there are two kinds of combinations. They're called series and parallel combinations. Okay, so there are two kinds of combinations. And those are series and parallel. So let's start with series combination. Okay, this is a case where resistors are connected in a single line. So for this kind of combination, resistors are connected in a single line. So let's say we have three resistors in series. That's what it looks like. Resistor 1, resistor 2, resistor 3. These resistors are said to be connected in series. Okay, So that's what you mean by series combination. When resistors are connected the same line, it's said to be series combination. Now suppose this is connected to a potential difference delta V. Delta V, okay? So we want to look at the defining properties of this kind of combination. Defining properties, okay? First, let's look at the current, okay? Now, the current, you see, the same current crosses all the resistors. So the total current I is the same as current crossing R1, the same as current crossing R2, is the same as the current crossing R3. So we can say total current equals current through resistor 1 equals current through resistor 2 equals current through resistor 3, and there are more resistors, the same pattern follows. So this is the first defining property for a series combination. All the currents are equal. And then let's look at the potential differences. Now remember, potential difference has to do with work, okay? Because remember, the change in potential energy is the negative work done, all right? And change in potential energy is related with potential difference. So the work done to go from here to here is the sum of the work done to cross this resistor, the work done to cross the resistor, the work done to cross this resistor, okay? In other words, the potential difference from here to here is the same as the sum of the potential difference across this resistor, the potential difference across this resistor, and the potential difference across this resistor. So you can say that the total potential difference delta V equals to the sum of the potential difference across resistor 1, potential difference across resistor 2, and potential difference across resistor 3. Okay, so these are the two defining equations for this kind of circuit. Now our goal is to get an expression for the equivalent resistance, that is the single resistor that can replace this combination without changing anything outside, okay? So let's define what we mean by equivalent resistance. We're going to use Req, it's represented, okay? So this is the single resistance that can replace the combination, without changing anything outside, okay? Without changing anything outside. So the combination without changing anything, okay? So it's defined to be total potential difference divided by total current, okay? So we have the following. Req is total potential difference divided by total current, okay? So the goal is to get an expression for this equivalent resistance in terms of the resistances, okay? So we're going to start from the second equation, okay? So the second equation states total potential difference equals the sum of potential difference across resistor 1, the potential difference across resistor 2, potential difference across resistor 3. Now this one is equivalent resistance times current, okay? So this is current times equivalent resistance. This one is from Ohm's law, current times resistance, Ohm's law, current times resistance, and Ohm's law, I3 times R3. But remember, all the currents are equal, okay? So we can just replace all of them by I. They're all equal to I. So this equals I times R1 plus I times R2 plus I times R3. So you see the current cancels out from this equation, and we get the following formula for equivalent resistance: R1 plus R2 plus R3. If there are more resistances, the same pattern continues. Okay, so for series combination, the equivalent resistance is the sum of the individual resistances, right? This is for series combination. All right. Now let's look at an example. Suppose you have the following circuit. Let's say this is a 6-volt potential difference, okay? And then this connect to the following resistors. Let's say this is a 2 ohm resistor. Let's say this one is a 4 ohm resistor, okay? So let's ask some questions. Let's say A. Calculate, let's say, the current through the resistors. Okay, now we can simplify this circuit because we can combine this in the single resistance. All right, so if you combine in the single resistance, Req is R2 plus R4, okay, where R2 equals 2 ohm and R4 equals 4 ohm, okay? So the equivalent resistance is 2 plus 4, that is 6 ohm, okay? So we can simplify this circuit in the following. We've got delta V equals 6 volt over here. Now we have combined these two resistors into single resistance, which is Req. Req equals 6 ohms, okay? Now we can calculate the current using Ohm's law. This is the total current in the circuit, all right? And the total current is this potential difference, delta V, divided by Req, okay? The total current is delta V divided by Req, and that is 6 volts divided by 6 ohms. We have 1 amp, okay? Now we go back to this circuit over here. You see the currents through here are equal to total current, right? So we have I2 equals I4 equals I equals 1 amp. So all the currents are equal to 1 amp, okay, because they're connected in a single line over here. Now let's calculate the potential difference across each resistor. P. Calculate the potential differences across the resistors, across the resistors, okay? So looking for V2 question mark, V4 question mark, okay? So obviously V2 would be I2 times R2. Now the current is 1 amp. The resistance is 2 ohm. So you get 2 volts, okay? So delta V2. Delta V4 equals I4 times R4, and that is current is 1 amp. This is 4, so we get 4 volts. Okay. Now let's test the equation. Delta V equals delta V2 plus delta V4. Okay. We know this is 6, so you've got 2 plus 4, checks out. Okay. All right. Now we're going to look at another type of combination, which is parallel combination. Parallel combination is branched combination. This is branched combination. Branched combination. So resistors connect like this, are said to be connected in parallel. Okay, so let's call this R1, let's call this R2, let's call this R3. Okay, now suppose this this combination is connected to total potential difference delta B. Okay, and once again our goal is to get an expression for the equivalent resistance, that is single resistance that can replace this combination. All right, so first look at the defining properties. Defining properties. Now these are conducting wires. You can assume the resistance of these conducting wires is 0, so that what that means is there is no potential drop across a conducting wire. That is, all these points are at the same potential on this side. All these points over here, same potential. All these points on this side, same potential. So that means is the potential difference across this battery is the same as the potential difference across resistor 1, the potential difference across resistor 2, and the potential difference across resistor 3. So we have first defining equation, that is the total potential difference equals potential difference across resistor 1 equals potential difference across resistor 2 equals potential difference across resistor 3. Okay, now let's look at the second defining equation. Now if you assume charges are carried by positive charges, what's going to happen is the positive charges are going to be repelled by this terminal and attracted by this terminal over here. So they're going to move this way. Okay, this is the current I, but once it gets over here, it has 3 different ways to go through. Okay, so they're going to split. Some of them will go this way, some of them will go this way, some of them will go this way. Okay, so you have currents through 1 over here, you've got currents through 2 and currents through 3, and then they will combine over here and then add up to I again. Okay, so the sum of these currents should be equal to total current. Okay, so the second defining equation is the total current equals to the sum of the currents through resistor 1, currents through resistor 2, and currents through resistor 3. Okay, and there are more, the same pattern continues. So these are the 2 equations which are the defining equations for this kind of combination. Okay, once again our goal is to obtain equivalent resistance. Remember, equivalent resistance is total potential difference divided by total current. Okay, so we're going to start from the second equation. So let's start from the second equation. It says total current equals the sum of the currents through the individual resistances plus I3. Okay, now let's use Ohm's law. The total current is total potential difference divided by equivalent resistance. This one is potential difference across resistor 1 divided by resistor 1. This is potential difference across resistor 2 divided by resistance 2. Potential difference across resistor 3 divided by resistance 3. But remember, all these potential differences are equal. Okay, so they'll just cancel out. Okay, maybe let me write again. So we've got delta V over Req. This equals delta V over R1 plus delta V over R2 plus delta V over R3, because all these potential difference are equal to total potential difference. So you see this delta V cancels out and we get the following equation. The inverse of the equivalent resistance equals the sum of the inverses of the individual resistances. Okay, and there are more resistances, the same pattern continues. So this is a formula for calculating the equivalent resistance of resistors in parallel. Or if you want, you can write this one as taking the inverse of this equation as 1 over R1 plus 1 over R2 plus 1 over R3 and so on, and then the power of -1. Probably this is an easier version when you use your calculator. Okay, now as you can see, this equation is cumbersome, but if you have only 2 resistors, it can be simplified. So let's simplify it for 2 resistors. For 2 resistors, we have the following: 1 over Req equals 1 over R1 plus 1 over R2, and so our LCM is R1 R2, and we get R2 plus R1. Okay, but this is the inverse, so we take the inverse of both sides and we get the following formula for equivalent resistance of 2 resistors. Now this formula, product over sum, works only for 2 resistors. If you have 3 resistors or 4 resistors, it doesn't work. Only for 2 resistors. Only for 2 resistors. Product over sum is only for 2 resistors. All right, let's consider an example. Suppose we have, let's say, a 6-volt battery over here connected to 2 resistors in parallel. Okay, let's say this is 2 ohm resistor, let's say this is 4 ohm resistor. Okay, so let's call this one R2. R2 equals 2 ohm, and let's call this R4. R4 equals 4 ohm. Okay, so let's ask some questions. A, calculate the potential differences across the resistors. Okay, so we're looking for delta V2, potential difference across resistor 2, delta V4, potential difference across the 4 ohm resistor. Okay, but we know that for a parallel combination, all the potential difference are equal. Delta V2 equals delta V4 equals the total potential difference, which is 6 volts. So all these potential difference are 6 volts. All right. B, let's say calculate the currents across the resistors. All right, so we want to calculate the currents through the 2 ohm resistor and the current through the 4 ohm resistor. Okay, so using Ohm's law, we have I2 equals delta V2 divided by R2. Okay, so this is 6 volts and this is 2 ohms, so we have 3 amps. Okay, I4 is delta V4 divided by R4, and that is 6 volts divided by 4, and that is 3/2 amps. Okay, And so the total current, you see, is I2 plus I4. That is 3 plus 3 over 2, or 9 over 2 amps. Okay, so let's test this using the formula for equivalent resistance. We can also calculate I from delta V divided by Req. Okay, now this is parallel combination, so Req equals product divided by sum, okay, plus R4. So that is 2 times 4 divided 2 plus 4. So that is 8 divided by 6, or 4 over 3 ohms, right? So using this formula, we get delta V, which is 6, Req 4 over 3, that is 18 over 4, or 9 over 2 ohms. So you see, they match. See these two? You can do it in 2 different ways. All right. Next, we're going to look at parallel series combination. Parallel series combinations. That is circuits involving parallel and series combinations. We'll just demonstrate this by means of an example. Suppose we have the following combination. Let's say all the resistors are 2 ohm resistors. All the resistors, this is an example. All the resistors are, let's see, 2 ohm resistors. The question is, calculate the equivalent resistance. The equivalent resistance. Okay, suppose you have the following circuit. You've got a 2 ohm resistor over here, and then maybe we have a 2 ohm resistor, a 2 ohm resistor, another resistor over here, and then 2 resistors connect like this, and then another resistor like this. Okay, we want to find the equivalent resistance of this combination. Okay, so as you can see, we have some parallel and series combination over here. So we're going step by step. You see these resistors over here, they're connected in parallel, right? So that's product over sum. This is 2, this is 2. So you've got 2 times 2 over 2 plus 2, which is 4 divided by 4, 1 ohm. So we can replace this by 1 ohm. This one is in series. You see this combination over here is 2 plus 2 equals 4 ohm. Okay, so we can replace this combination by 4, this combination by 1, and we have the following. We've got this 2 ohm resistor over here. Now this combination is 1 ohm. Okay, and we still have this 2 ohm resistor over here. Okay, and then from here we have this combination over here, which is 4 ohm. This is 4 ohm over here, and then these are connected like this, and then we have this 2 ohm resistor over here. And now we see that these two resistors are in series. Okay, so we can combine them together. That is 1 plus 3. Okay, 1 plus 2, that is 3 ohms. Okay, so we can simplify this circuit to the following. We've got 2 ohm over here. Now we have combined these two into one resistor, 3 ohm resistor. Okay, and then over here we have 4 ohm resistor, 4 ohm resistor, and then over here we have a 2 ohm resistor. All right, now we see that these two resistors are in parallel. Okay, so we can combine them. That is 3 times 4 over 3 plus 4, that is 12 over 7 ohms. So now we can simplify this circuit into this one. We get 2 ohm over here, and then this combination is 12 over 7 ohm. So we have this 12 over 7 ohm, and then we have the 2 ohm resistor. Okay, 2 ohm, 2 ohm, and 12 or 7 ohm. Now we have 3 resistors in series. Okay, and for series, all we do is add them up together. So the equivalent resistance is 2 plus 12 over 7 plus 2, or 4 plus 12 over 7, that is 28 over 7, plus 12 over 7, that is 40 over 7 ohms. So this is the equivalent resistance of the combination. Now let's look at a circuit involving parallel and series. Alright, so let's look at an example. Suppose we have this battery, again let's say 6 volts, 6 volt battery. It's connected to, let's say this is a 1 ohm resistor, and then we have maybe a 2 ohm resistor over here, a 3 ohm resistor over here, and then it's connected like this. Alright, so the question is calculate the currents and potential differences across the resistors, okay, so we're going to simplify these circuits. Let me call the 1 ohm resistor R1, okay, the 2 ohm resistor R2, this 3 ohm resistor R3. So I'm going to use subscript 1 for this resistance, subscript 2 for this one, subscript 3 for this one. Okay, so now I see these 2 resistors are in parallel. Okay, so I can combine them into a single resistance using the formula for equivalent resistance, which is product over sum. Okay, so let's call the equivalent resistance of resistors 2 and 3. Let's call like this. That is R2 R3 divided by R2 plus R3, right? That is 2 times 3 divided by 2 plus 3, that is 6 over 5 ohms. Okay, so we can simplify this circuit into the following. We have the delta V equals 6 volt over here. We have the 1 ohm resistor over here. Now we have combined those 2 resistors into 6 over 5 ohm. Okay, so we have a simplified circuit. Alright, once again we can simplify it because we combine these 2 resistors, they're in series. Okay, and that is 1 the equivalent resistance is R1 plus R2 3 because they're in series. That is 1 plus 6 over 5. Okay, so that's 5 over 5 plus 6 over 5, or 11 over 5 ohms. Okay, so these resistors can be replaced into this single resistor circuit. Okay, so we have the following. So we have delta V equals 6 volt, and this one is Req equals 11 over 5 ohms. Now we can calculate the total current in the circuit. The total current in the circuit is delta V, total potential difference, divided by equivalent resistance. Okay, and that is 6 over 11 over 5, or 30 over 11 amps. So it's the total current in the circuit. Now look, let's go back to this circuit. These 2 resistors are in series, so their current should be the same as the total current over here. Okay, so we're going to say I1 and I23 are the same as this current over here. Okay, so since R1 and R23 are in series, since R1 and R23 are in series, we can say that I1 equals I23 equals total current, and that is 30 over 11 amps. Okay, 30 over 11 amps. So we have the current through the resistor 1 is 30 over 11 amps. Okay. All right. Now again, we can go back to the previous circuits over here. You see R2 and R3 are in parallel, so they should have the same potential difference as R23. Okay. So since R2 and R3 are in parallel, we can say that the potential difference across resistor 2 equals potential difference across resistor 3 equals the potential difference across R23. Okay, but remember, this one is the current through 2,3 times the resistance to 3. Okay, the current is 30 over 11, and the resistance of the combination of 2 and 3 was over here, 6 over 5. Okay, R23 6 over 5, 6 over 5. So we have maybe by 5.1 by 5.6 we get 36 over 11 volts. Okay, so it follows that delta V2 equals delta V3 equals 36 over 11 volts. So now we have the potential differences, so we can calculate the currents. Okay, so let's start with delta V1. Delta V1 equals for current, I1 equals delta V1 over R1. Delta, we have the current for I1, so let's calculate delta V1. So we got delta V1 equals I1 times R1. The current is 30 over 11 amps, and the resistance is 1. So we get 30 over 11 volts. And for this, we have the potential differences. Let's calculate the currents. So I2 equals delta V2 divided by R2. Okay, so the potential difference is for delta V2 is 36 over 11 volts. So this one is 36 over 11 volts divided by the resistance of R2, which is 2. Okay, so we get 18 over 11 volts. And I4, same thing, is delta V4 divided by R4. The potential difference is the same like this one, 36 over 11 divided by 4, and that is 9 over 11 volts. So that completes the problem.